Hello, everyone. My name is Dominik Sisejkovic, and I'm a research assistant and chief engineer at the Chair for Software for Systems on Silicon at the RWTH Aachen University in Germany. And I'm happy to tell you today a little bit about the topic of machine learning versus hardware integrity protection, who will prevail. So let's start with the motivation. As you might already know, nowadays, the integrated circuit supply chain has a very globalized nature. Which means that many different third parties are actually involved in both the design and fabrication steps of actual hardware. This has unfortunately led to a loss of trust and assurance between the involved parties. And of course, this has then resulted in potential security issues, one of which is a very serious one that we know as hardware Trojans. So what are hardware Trojans? Hardware Trojans can basically be defined as malicious design modifications, which are injected into the hardware during design or fabrication steps. And these malicious design modifications can actually lead to various attack vectors. Typically, we consider attacks such as information leakage or performance degradation, or for example, also a denial of service attack. Obviously, if we place hardware Trojans into the right scenario, they can actually lead to very, very dangerous situations. For example, you could imagine a denial of service attack hardware Trojan, which is placed deeply within a processor design, which is a common component in many different modern vehicles. And obviously, in a moving vehicle, a denial of service attack can actually result in dangerous consequences. So the very important question today that we have is how can we actually deal with hardware Trojans? Well, one way to deal with hardware Trojans is to try to detect them. However, as it turns out, detecting hardware Trojans is in principle very, very difficult because it is very, it's a complex task to actually come up with a detection method that is able to efficiently detect all kinds of hardware Trojans on many design levels. Hence, detection at this point in time is still developing and it's still very inefficient. So the second option to deal with hardware Trojans is actually to try to prevent them by design. And that is also something that I've been working on in the last couple of years. And actually a lot of research has been done for more than a decade to develop different techniques to prevent hardware Trojan insertion, among other objectives. So let's take a quick look at the untrusted integrated circuit supply chain to understand a little bit better where things could potentially go wrong. So here you can see a very abstract view of the IC supply chain. At the beginning, of course, we have some specification of the to be developed hardware. And based on this specification, a given RTL design is compiled. This RTL design then goes through different steps, which include logic synthesis and physical design steps. Afterwards, the designed chip ends up being transferred to the fabrication, where it's put into silicon, and the silicon chip is afterwards packaged and assembled, and finally distributed and integrated in many different devices. So in this particular IC supply chain, typically what we consider as the window of vulnerability where things could potentially go wrong is the following one. So the red box here shown on the slide, which includes the physical design and the fabrication. So why the physical design and the fabrication? Well, as I mentioned at the beginning, we always considered third parties as untrusted entities, so entities which could potentially change the design. And as it turns out, most protection mechanisms that we know of today actually perform or are executed on the gate level. So which means that everything after this gate level could potentially be protected, but not before. Hence, in many different scenarios, many different companies, especially those which don't really have so much experience or so much knowledge to perform, for example, physical design, have to outsource this step to an external design house. And as I say, external, that basically means it could be an untrusted entity. Okay, so if you consider the physical design and the fabrication, these are our malicious entities. And in the rest of the slides, when I say malicious entity, it could be any of these two within this window of vulnerability. And that is exactly the place where a hardware Trojan could potentially be injected. Okay, So now we've learned where things could go wrong in this integrated circuit supply chain. So let's take a look at what kind of hardware Trojans we could actually potentially protect against. So in principle, there are two types of hardware Trojans. And here on the slide, we will consider a very, very simple example. So when the malicious entity receives our design, so it's at the beginning, it's basically an unknown design. So there is no reason for us, for the original designer, to tell the external design house or the foundry what the chip is used for. Right? That's not really important for the fabrication step. So the malicious entity actually receives an unknown design, and this unknown design can be, in principle, infected by a hardware Trojan without any need to perform reverse engineering. And reverse engineering in the sense means that the attacker doesn't have to understand the functionality, understand the structure, or even the use case of this hardware that is going to be produced. And in this design independent scenario, the Trojan, which is design independent, can be very easily injected. So here you see a small example of a hardware Trojan with the typical components of Trojans that we know of. So typically there are two components of a hardware Trojan. One is the trigger and one is the payload. The trigger basically is a component which listens to some signals or to some state in the circuit. And once it detects the activation sequence, it actually tells the payload to execute the malicious functionality. So the payload then actually performs some change in the circuit, which can result in various attack vectors. However, in this scenario where we consider that the malicious entity does not have to perform any kind of reverse engineering, this Trojan can be implanted basically like a random fault. So you can just pick any location in the circuit, insert any form of hardware Trojan, and kind of hope for the best, or basically hope for the worst in terms of the attacker. However, this will probably result in an unknown attack in an unknown environment. So the impact of such a hardware Trojan will probably be not as high, and the probability that we will detect such a fault is in turn increased, because it might lead to a very obvious fault. And unfortunately, these hardware Trojans are in principle something we cannot protect against, because they can always be injected into the design, since no real effort is required by the malicious entity. So the second type of hardware Trojan that we actually consider protecting against are design-dependent hardware Trojans. So these are hardware Trojans where the designer, the malicious entity, actually has to perform some form of reverse engineering. And in that case, the same Trojan that is shown here on the slide must be meticulously placed in a very specific position in the circuit, such that a predictable and controllable attack is performed in a known environment. And obviously, this effort that is required by the malicious entity in turn can be paid off in terms of a very high impact attack. But these design-dependent Trojans are in principle something that we can protect against. So why? Well, as you can see, there is a specific effort by the entity in terms of reverse engineering, which is required to perform the insertion. So the key word here is reverse engineering. So we need to increase the complexity of reverse engineering to actually be able to protect against such Trojans. Okay, so keeping this in mind, that reverse engineering is kind of the key player in this process, we basically can come up with a way to protect against the insertion. So typically, if we don't have any kind of protection mechanisms, where in the scenario where we consider meaningful, controllable, and design-specific hardware Trojan insertion, then the reverse engineering flow typically looks like that. So at the beginning, we have this reverse engineering, and reverse engineering is a very large term. It's a very big word. But in principle, what we consider reverse engineering is the process of or two steps. So one is to actually come back to a design format, such as a netlist, where we can actually operate on. And second is actually to identify all the different components and the functionality of this netlist, because this functionality and this knowledge about the different components can actually be utilized to define a very impactful hardware Trojan. And that is the flow that we need to prevent, or which basically complexity we need to increase. And that's exactly where we want to operate on. So we want to imply different hardware design protection schemes, such as that whatever comes afterwards, it becomes more difficult for the attacker. And remember that we have this window of vulnerability, which is often given in 3 to 6 months. So there is a limited time window where potentially something could go wrong. Okay, so in terms of design protection methodologies, there have been many proposals. And one of these proposals is actually logic locking. So logic locking, also sometimes known as logic obfuscation or logic encryption even is a very popular countermeasure for hardware Trojans. And in principle, it can help with IP protection as well. So how does logic locking actually work? So logic locking actually typically works on a gate level netlist. So it works on a gate level. Such as the one here shown on the left-hand side, where we have an original circuit given in the typical gate level netlist format. And what logic locking tries to perform is it inserts different changes, so it performs different changes on the original circuit by implying or injecting new gates, which we typically call key gates, because they are connected to a set of key inputs. And that's exactly the key point of logic locking. So since the original circuit has been changed through the inclusion of new functionality or through the inclusion of changes that actually are bound to a secret key, the locked circuit now becomes dependent on this secret key, which we do not have to share and which we shouldn't share with the malicious entities. And this has a profound effect now for the hardware Trojan insertion, because the malicious entity actually has to figure out the correct key, the value of the key, to be able to reverse engineer the circuit and go back to the original one. So this is a very important step, because only once we have the original circuit, we can actually perform the insertion of design-dependent hardware Trojans. And that basically means that the engineering effort to perform reverse engineering is now increased. And that's what we wanted to achieve at the very beginning. And in terms of logic locking, there has been a tremendous amount of work in the last more than a decade with many scheme proposals, with many attacks. And in principle, we will not focus on all of them today. We will just take a very small snapshot of the attacks which are relevant to machine learning. But before we do so, it is very important for you to understand what the actual attack model is in terms of logic locking and in terms of this technology. So typically, we assume that the malicious entity, so the attacker, has the following capabilities. So the attacker is able to access the locked gate level netlist, which is of course a given one, because if the malicious entity is the design house, they will receive the netlist in form of the locked gate level netlist. If it's the foundry, they will receive the locked, basically GDS2 format of the design. But in both cases, it is possible to go back to higher abstraction levels, such as the netlist, or maybe even higher than that. So that's an assumption that we of course have to make. The second assumption within the attack model is the fact that the attacker is able to distinguish between regular and key inputs. So the attacker is able, for example, in this netlist here on the right, to understand that these are primary inputs, so the original inputs of the circuit, and these are, or in this case, this is the added key input. Of course, the scheme, so the locking scheme, should be clever enough such that even if the attacker knows this, he cannot simply remove what has been added to the original circuit or how the circuit has been changed. And this is a very big challenge that we have today, but I'll go into that in a second. And finally, the third assumption is the access to an activated Oracle IC. So this image here basically represents this activated IC. What does it mean? Well, it means that the attacker in principle could go and simply buy a copy of an activated chip, which has already been produced from the market. And this obviously only makes sense in a scenario where we have multiple batches, multiple production rounds of the same chip. And the chip, of course, is in that case already activated, because the designer, the trusted entity, can activate the chip once the locked design has been fabricated and returned back to the original design. And using this third assumption, we can actually divide all attacks into two classes. So the first class is the class of Oracle-guided attacks, and the second one is the class of Oracle-less attacks. Here, Oracle-guided basically means that the Oracle, so the activated IC, is available. This is, as I mentioned, often the case in a high volume production. So a production where we produce many, many different chips in many batches, in many production rounds. And in that case, the attacker could simply buy a copy of that chip on the market and then try to use it as an oracle. So to be able to put some input patterns, read out the right output values, and then use it as an oracle to actually figure out what the correct key could be. This assumes, of course, that you cannot simply read out the key from the chip, but that's maybe a story for another time. The second type, so the Oracle-less attacks, are attacks where the Oracle is not available. This is also, in our view, a more realistic one, so more realistic attack scenario, and it's typically deployed in a low volume production. A low volume production basically means that only a few chips are produced, or very little rounds in a small number of rounds of chips. And these chips are actually deployed in a high security scenario, which means that not everyone can simply buy a chip on the market, but it's actually very hard to acquire a copy. Okay, and using this attack model and this classification, a tremendous amount of proposals have been done in literature, both on the schemes and the attacks side. So in terms of schemes, as I mentioned, many proposals have been done with many different functionalities, from XOR gates, AND/OR gates, functionality stripping, diverse combinations of those. So the details here are actually not important for this talk. As well as many different attacks have been applied as well, from functional, structural, side channel attacks, and diverse combinations of those too. And what we are looking into in the last, what we have been looking into in the last couple of years is, okay, so across all these schemes and across all these attacks that we already have seen, what is actually the impact of machine learning? So nowadays we have access to easy to use and very efficient machine learning algorithms. We have dedicated hardware for that. It's very easy nowadays for anyone basically to use very efficient and very powerful machine learning models. So can we utilize actually machine learning for maybe breaking logic locking or trying to improve it? So that's a very interesting question that we see nowadays in the research community. And it seems like it's opening up a new wave of logic locking design. Okay, so considering that we have now all these different kinds of machine learning models, the very big question is, okay, what can be actually exploited by machine learning in terms of logic locking? Well, in principle, there are two things that could be exploited. So if we consider the netlist which is provided, so the locked netlist which is available to the attacker, a machine learning model could try to analyze the structure of the netlist that is associated to the key input. So if the structure can be found, and it can be found, because if you remember, the one of the assumptions was that the key input is identifiable for the attacker, then the attacker could in principle track this key input and try to extract a part of the netlist or some sub-netlist that is somewhat associated to this key input. And then the question is, okay, if I have many different samples of such subgraphs which are associated to a single to a specific key input and key input value, potentially I could actually learn, if I see such an unknown subgraph, I could learn to predict what kind of key input value should be associated with that subgraph. So that's one way to do it. So we can try to associate structure with the key or with the key value. The second approach is in terms of an Oracle guided attack. So where the Oracle is actually provided. If I have an activated IC, I could potentially try to associate the input-output behavior with the key. So if I have an Oracle on my desk and I can actually set some inputs and read some outputs, maybe I can utilize this behavior and check whether I can figure out, or whether the machine learning algorithm could figure out what key should be given here on the left-hand side, so to the actual netlist, such that the input and output behavior is preserved when comparing to the Oracle. And using this, these two worlds, so this structural and functional or behavioral description of the locked design, we can actually develop many different machine learning attacks. So let's consider a few of those which are well known at the moment in the scientific community. So in terms of Oracle-less attacks, so attacks where the Oracle is not provided, but only the netlist is provided, one of the first attacks in this class is known as SAIL. And here you can also later take a look at the papers if you're interested. So how does SAIL actually work? So SAIL takes as input the target netlist. So that's the locked netlist, which is provided to the malicious entity without providing, of course, the correct key. It's just the locked netlist. And what SAIL tries to do is it extracts the localities. So localities are basically these subgraphs which are associated to a key input. And then it tries to predict whether the synthesis process, so the logic synthesis process, has implied any form of change into the locked design. So why is this important? Well, when we consider a very simple logic locking scheme, which inserts, for example, XOR gates and XNOR gates. So you can simply think of the simple scheme which inserts an XOR gate, which is coupled to a key input. And the other input is simply a randomly selected input from, randomly selected wire from the design, and it simply buffers that value. So if the correct key is provided, then this value will be equivalent. It will be always preserved. And in terms of the XOR gate, it should be, of course, a 0. And in terms of an XNOR gate, it should be a 1. Then this value is actually buffered within the chip. However, if the wrong key is provided, then of course the design will not perform as intended, as originally intended. So once such an XOR XNOR scheme is deployed on the locked design, typically we have to perform another round of logic synthesis to integrate everything into the locked design and to make sure that these XOR and XNOR gates are actually blurred away, so that they are actually merged into the circuit. And the SAIL attack has noticed that it is possible to actually design a machine learning model which can learn to reverse this process, to reverse the synthesis process, which means that it can predict the locality which has been there before another round of logic synthesis has been performed. And if that is possible for this specific scheme of XOR XNOR based logic locking, it is relatively easy then to predict the key. So basically SAIL tries to reconstruct pre-resynthesis designs, or in other words, it tries to figure out how did the locked IC look like before resynthesis. Another attack that we developed here at my institute is called Snapshot. It works in a very similar fashion. However, we have realized there is no really need to develop a machine learning model that can or that can reconstruct the netlist before resynthesis, but we can actually look at these localities, at these key associated localities after the resynthesis process, and immediately try to match them with the correct key value. So SAIL is actually more powerful in that sense, and it actually tries to answer the question which key bit is expected for a given local structure. So it tries to learn local hardware structural patterns. A third attack that has been developed in this domain is known as GNN unlock. It's also a very interesting attack. It uses, as the name suggests, graph neural networks. And in comparison to SAIL and Snapshot, it actually doesn't try to predict the key value, but it actually tries to predict if whether a specific node that is currently being evaluated is part of the original design, or whether it's part of the locking circuitry, so what has been added. So in that sense, it tries to identify the locked key gates, so the key gates that have been inserted into the design, and basically remove them. So it's a very interesting attack as well. So in that case, it tries to answer the question, is a node really part of the locking circuitry or the original design? And the fact that these attacks actually work quite well, somewhere between 70 to even up to 100% of the correct key or the nodes can be identified. Well, that tells us that all the effort that we have seen in the last 10 years in this domain have actually missed this very important question. They have missed the fact that the key is still associated, or the key value is still associated with some structural aspects of the circuit. And that is something we have to work on. So that's something we have to try to fix. Okay, so these were Oracle-less attacks, and as you can see, they mostly focus on structural aspects of logic locking circuits to try to deduce something about the correctness of the key itself. In terms of Oracle-guided attacks, I will just mention a few of those as well. So one of the first attacks, which uses machine learning-based models for key retrieval, is known as SURF. Some recent ones are as well GenUnlock and the PSO attack. I will not go into too many details, but basically the idea of these attacks is that we can use the Oracle, so the correct IO mapping, and the netlist to try to refine the key based on some output behavior. So the big question that these attacks try to answer is, how does a change in the key impact the correctness of the output? So basically what the attacker can do is he can try to change the key inputs, so the key values of the key inputs in the target netlist, and use the Oracle to guide this process. And in terms of SURF, it is a very custom-made heuristic optimization with simple bit flips, and then the behavior of the target netlist is compared to the Oracle. Or in terms of GenUnlock and PSO attack, GenUnlock is using a genetic algorithm for this process, while PSO is using a particle swarm optimization algorithm. So these two are actually coming from the domain of soft computing or evolutionary computation to actually optimize this search process. And as it turns out, they actually work quite well too, which means there is a clear correlation between the correct key value and the behavior of the chip. And that is something we again have to resolve. Otherwise, as long as there is an association, as long as there is a correlation, it is possible to perform such an optimization, such an heuristical search for the key. Okay, so we have seen some Oracle-less attacks. We have seen some Oracle-guided attacks in machine learning. So an interesting question is, of course, how can we try to prevent such attacks? Well, as it turns out, so far there is not much we can really do, because only a few solutions, or a handful of solutions, have been proposed in the literature that target machine learning-based attacks. One of them is also DMAX, so that's one that we developed in my chair as well. If you're interested, all the papers are listed below. So how do these schemes actually work? So we are considering DMAX, Unsale, and Saro. So these are one of the new ones which try to resolve this machine learning attacks on logic locking. Obviously, due to timing limitations, I will not go into details, but the very simple idea is as follows. So we need to be able to create equal local changes for both key values. That basically means that any attack that tries to associate a given subgraph of the netlist with a correct key must encounter a very confusing training set in order to fail in the prediction. And this is obviously the case if we have two local changes which are equivalent in structure, but which are both associated with different key values. And in practice, you can just imagine having two images, for example, where both images are labeled, where one image is labeled with the key value 0 and one is labeled with the key value 1. Obviously, in that case, it is very, very difficult for the machine learning model to make a correct prediction, because at the end of the day, it's just a random choice. Another option to try to prevent machine learning attacks is by decoupling the key value from the local change, which means whatever we are implying, whatever we are changing in the circuit should not depend on the key value in the structural sense. That is, for example, how DMUX is actually working. And another aspect is, of course, randomness. We need to apply randomness in terms of how we perform the change in the locked netlist, and of course, where we perform the change in the locked netlist. And if we can actually come up with a scheme that makes sure that all these requirements are fulfilled, then a machine learning model will most likely fail in predicting the correct value. However, we still have another open challenge, and that is a very, very interesting question, actually. So even if we lock all these circuits, the question that remains is, can we still guess the hardware, or basically the circuit functionality, regardless of the protection mechanism? So how much change do we actually have to imply such that a malicious entity is maybe not able to detect what the circuit really does, so what the functionality of the circuit really is? And of course, in long term, this could be also a machine learning model that tries to automatically deduce the functionality, but that's still an open question. So to finalize my talk, we are very sure that machine learning in all its forms will be a key player in the following years in both the security evaluation of logic locking as well as the design of next generation schemes. So we are very much looking forward to this ML era of logic locking, where machine learning is actually playing against hardware protection. So thanks a lot for listening in. And if there are any questions, I'm happy to answer.